Everything is
So the title of the presentation is the weather data-driven models for regional energy forecasting, and it's the results I present today were obtained in the frame of my PhD research project, and the project aims to apply forecasting data-driven models for photovoltaic energy production and for forecasting energy consumption in Romania using meteorological data and machine learning techniques. The main goal is to forecast the amount of photovoltaic energy production at particular sites and forecast also energy consumption and energy production on a national level in the frame of climate variability and climate change in order to support effective planning and management of energy resources at national and regional level. The specific objectives of the project were to analyze the correlations between weather, climate, and photovoltaic production and energy consumption. Another specific objective was to apply the machine learning models for forecasting the photovoltaic energy production and to apply machine learning models for forecasting at the national level the energy consumption. And the last objective was to evaluate the future trends in energy consumption in the context of climate change. For me and in general, the project is very relevant as it would contribute to optimizing the energy system, the energetical national system in the context of the rising of photovoltaic capacity and climate change, and to support the transition to a smarter grid in integrating all these renewable energy sources. As you can see in the graph here on the lower right, the share of renewable energy grew quite fast in the past 10-15 years. It almost doubled since 2010. Here we're in 2024, and the trend is on a growth slope. And even more, we can see here the graph for photovoltaic share of energy in Romania and photovoltaic production. The estimates are that the photovoltaic energy will grow by more than 4 times in the next 3 or 4 years. So the pressure on the national grid will be quite big. And apart from the estimates on the energy the installed capacity, we have some problems. There will be some problems related to forecasting the amount of energy. We all know that photovoltaic and wind energy are not constant and are not available on demand, but rather depend on the weather conditions, and thus there are very complex interactions between the weather conditions, the energy demand, and also the infrastructure. So we need more complex models than we have today to balance the supply and the demand. As I mentioned, the goal of the project is the development of prediction analysis tools for energy planning in the context of climate change. And for this, we have a multidisciplinary approach using data and methods from meteorology, climatology, energy, and machine learning. And we are doing a multiple level integration. We are doing this analysis and forecasting at the level of photovoltaic farm, so at point scale. We will do modeling at national and regional level, and also regional national scale. We'll do projections based on climate scenarios. For this, we first collect data and we process it, weather data, climate data, energy data. We apply various prediction models. We do the validation and optimization of the models, and then we apply the models on future climate scenarios. This is the conceptual scheme of the project. So we aggregate historical weather data with photovoltaic data. We aggregate weather data with energy consumption data. We are using the machine learning models to analyze the correlation between weather conditions and energy consumption, energy production. We are doing predictions. We evaluate the performance of the models, and we have this feedback loop. And the models that perform best will be used together with numerical weather outputs, so with forecasting data, not historical like we did in the first stage, and together with climate scenarios, in order to analyze the impact of the predicted climate scenarios on energy production and consumption. We are using several data sources, data from our national network of weather stations. We used only the stations below 800 meters, which are relevant for both the energy production and energy consumption. Several parameters, the most important, solar radiation and air temperature. We use data from 4 different years, and for the daily average, we use data since 2008. For photovoltaic data is of interest. This Solcast is a paid paid database with 15-minute data reanalysis data. For the photovoltaic data, we used Unisolar data. It's a database, free for access database used for specifically built for machine learning models for prediction of photovoltaic production. We have for different locations in Australia, we have different meteorological and energy data. We used 2 years to full years. For national analysis, we use data from Transelectrica, data aggregated at the national level every 15 minutes from 2007 to present day. And we also used in our analysis several indices. In fact, 2 important indices, the heating and cooling degree days. For the analysis, we tested several machine learning models, random forest, XGBoost, AANs, linear regression was a baseline, and several indices and coefficients for assessing the performance of the models. First, we did tests related to photovoltaic generation in specific points. For this, we used the unisolar data. We had almost 70,000 entries, 2 years, 15 minutes intervals. 80% of the data was used for training and 20% for testing. We had good meteorological data and energy production in each of these points represented here. The best results that we got were achieved using the random forest models, and the most important parameter was the global horizontal irradiance. This was more than 80% relevant for the model. We got some decent scores. The models were not optimized. It was just the first stage of the research, and you can see that the highest errors we got, especially here is not clear, but we got when especially close to zero energy production at sunrise and sunset, and at around noon, when because temperature highly affects the energy production, and the correlation between solar irradiance and energy production is not good here. The efficiency of the panels actually decreased, and yeah, the model, since it considers the irradiance as the most important parameter for prediction, is not doing quite well here. And you can see here from the results some of the performance of the model that we used, and we can see that the best results we get it's around here before noon and in the afternoon, and the worst results are when we have very high energy production, but as I said, this one is affected by temperature, and the performance of the model is not that good. Here you can see the graphics here. The graphics are here to show the correlation between solar generation here in red and various parameters. You can see here the global horizontal irradiance is closely correlated with energy productions. The other parameters, some of them, it's an inverse correlation. You can see, for example, the humidity affects a lot the production. Here we have also some results of the analysis when we were using the best results we got when we used 13 parameters, 13 features. The results were decent, also using only the global horizontal irradiance. You can see here that the best results we got for data in the afternoon. And yeah, here you can see that the random forest performed best out of the 4 models that we used. So the factors affecting the photovoltaic generation, as I said, the global horizontal irradiance is the most important. Very important is the time of the day, and using also the cycle, the hour of the day also improve the performance of the model. Perhaps if we have used more data than we used before, we would have gotten better results, as the models could have captured the sunset and sunrise moments where we had quite poor performance. Also problems with extreme values, as I said, low production and very high production, and including the temporal dependencies, increase the performance of the models. The second part of the activities were related to weather impact on the national energy graphic. I performed several tests with several models. In the end, the XGBoost regressor seemed to perform best, and I used it for most of the experiments. We performed analysis of prediction with and without air temperature. This was the parameter we used for the consumption graphic. We also we studied the correlations between the heating degree days and the cooling degree days with energy consumption. We investigated the impact of temperature threshold for HD and CDD on prediction accuracy, and we implemented and tested the model for predicting the photovoltaic production at national level using the global radiation data. We determined the complex relationship between the meteorological conditions and energy dynamics at the national level. We identified limitation at national level analysis in terms of the masking of local weather impact on consumption. So we only have data on a national scale. The energy data is on a national scale. But we failed to capture the impact of particular weather on particular regions, which many times is different. So we need to cluster. We need to somehow cluster the data, since we don't have regional energy data yet. And another impact is, it's because of the related to densely populated places. So they have these areas have a much larger impact on the global, on the national consumption level. So, as I mentioned before, we need to somehow cluster the data in order to capture weather impact on densely populated places where also the consumption is higher. And in this sense, it's evident that urban locations have a much bigger impact on the national consumption. So in future, we plan to use clustering techniques and perhaps to receive regional energy data for more precise analysis. Here we have some results. Here on the left we have a graphic with related to energy consumption. When in blue we have the actual energy consumption, and in red estimated energy consumption. As a methodology, we were predicting the energy consumption for the next 24 hours using based on the weather conditions. So we used the actual conditions, not the forecasted ones. So perhaps the model was performing better than in the case if we have used the predicted weather forecasting output. But we can see that the model performed decently with the production. The errors are higher, much higher, and the correlation between temperature and energy production is not that good, and this is clear because production depends on many factors. It's not only weather driven, and it depends on also decisions related to infrastructure and energy demands, while consumption has a high correlation factor with weather. So you can see here in the winter, the energy consumption grows. In the summer, in the spring and autumn, we have lower energy demands, and we have some peaks here on very hot days in July, August. And here we perform some analysis with and without temperature data. The models perform better when we use the temperature data. For production, we can see that there wasn't much gains using temperature data. Here we have some graphics also at the national level with the photovoltaic production. You can see that here we also use the radiance from the weather stations. You can see, and here on the right we also applied an offset, because we noticed that the model was the shape of the prediction was quite good, but we had this offset, and it was because of the increase in photovoltaic capacity. And here it's also a place for further analysis about this offset that we should apply from year to year, as the photovoltaic installed capacity will grow, as I mentioned at the beginning of the presentation, by almost fivefold. Other tests were performed for analyzing the correlation between the heating degree day and cooling degree day on energy consumption. We can see that we have a very low correlation between cooling degree day and energy consumption. So what that means is that on very warm days, the impact of energy is not that large like in the for the heating. So when it's cold outside, the energy consumption grows, but when it's very warm, we don't use that much energy for cooling the living spaces and working spaces. And we also observed that we had correlation with other indices that are mainly used as being most relevant for the cooling. It was considered in Romania 18 degrees, but actually we had better correlation, negative correlation with the cooling degree day, with the 10 degree cooling degree day, and for the heating degree day we had the best correlation with the 14 degree indices instead of the 20 degree indices. So we have some limitations related to the scale of the data that we used. We used data only at the national level, and it was masking the regional variations. The air temperature was the most important factor for the accuracy, but it was also very important the time of the day, and also the days of the week and national holidays. And the models are most, it's clear that they are much more valuable for estimating consumption rather than production, which depends on too many other factors rather than weather factors. The conclusions are that the machine learning models appear to be very promising for predicting the photovoltaic generation and also for estimating the national energy consumption. Thus, there probably will be used in the future for scaling and planning the national grid, especially in the context of the larger shares of renewable energy. We identified several limitations, mainly related to the data that we used. We need to use most definitely more granular data. We also identified factors that, other than weather, that are difficult to integrate in the models. Also, a problem will be with the big increase in the next few years of the share of photovoltaic energy in the national grid, and also we will have problems. The model will have problems modeling extreme weather events. And for the next activities, we'll cluster data. We'll try to use and get more granular data, and we will also test with other machine learning models, maybe more suited for our data, and in the end we'll use climate scenarios for future to understand the impact of future climate conditions on energy production. Thank you very much.